So we will continue today first chapter 10. Yesterday we introduced the method to do the LU factorization, and also we considered the case where we have to do pivoting. So in case we have to do any pivoting operation, we said that the pivoting operation should be also applied to matrix L and to P, which is the permutation matrix. Okay. In this way, at the end of the procedure, we will have the final U, L, and P matrices, and then we can use P to see what will be the changes that the B vector will undergo. Okay. So let us apply this method now for a certain case. So the case we considered yesterday was to start with the following system. So we want to solve for a system with the following matrix A times X equals to B. So in the first step, we said that before starting to be able to solve, the first step in LU factorization will be to decompose A into L times U. Okay, and to do so, we needed to do pivoting because the elements were not placed conveniently. So in the previous example, we considered the elements were perfectly placed. We don't need to do any pivoting because at any pivot operation already the element in the pivot equation is higher than all elements below. So no pivoting is required. On the other hand, in this example, we need to do several pivoting steps. So just to remind you, for example, we considered first the first equation as pivot equation, but it was not the most convenient one because when we compared to elements below it, 11 was the highest one. So we switched rows 1 and 4. Okay, and then when we are done with this procedure, we move to consider row equation 2 as pivoting equation, and also it was not acceptable because we have a 0 here, so we had to do another pivoting, and at the end we had also to do a third pivoting. So to track the pivoting that we are doing, we created a permutation matrix P. And just keep in mind that just for the first pivoting operation, we just did pivoting of rows 1 and 4 for P. But L, we didn't do pivoting for L because already L, we didn't complete anything in it. And in the first step, L, we don't have any element yet in it. So why we need to do pivoting for L if we don't have anything here? This is why just in the first step, we did only pivoting for P, while for L, since we don't have anything yet, we didn't do any operation. But in the next operation, when we did a pivoting a second time, now already L had elements, okay, had elements of the first column. This is why we did pivoting operation for L, and we did pivoting operation between rows 2 and 4 for P. And then when we conducted the third pivoting procedure at the end, also we updated L and P. Okay, so yesterday we were done with this process, and we end up with the following matrices for U. So this the final matrix for U was the following one. So this is the final U matrix. Okay, and as you can see in the final state, we have an upper triangular matrix, and all elements, due to forward elimination, all elements here were transformed to 0. For now, for L and P, these were the final L and P matrices. Okay, so now we will use this system. We will use L, U, and P to solve for X. Okay, how to do so? So what is different from the method without pivoting is just that now we replace AX in the system by P times A times X. And since we multiplied A by the permutation matrix because of pivoting, then also B should be multiplied by the permutation matrix P. Okay, so now when we want to solve, we cannot take B as it is. We should multiply it by P. And already P times A will give us L times U, the final lower and upper matrices we obtained by doing our operation. Okay, so now in the last step, to solve for X, what should we do? First, the first step will be to find the modified vector B by doing P times B. And then once we have the modified vector B prime, then we can now do the forward substitution first. What do we mean to remind you? What is the forward substitution? We consider that U times X is vector D. Okay. And we just say now the first equation to the first system of equations to solve is L times D equals to B prime. And since L is a lower triangular matrix, then we will do forward substitution. We'll do it in an example to see how. Okay, and once we find D, then we say that D is U times X, and we solve for X by backward substitution. So let us go in details over this method in this example. So first, I want to solve AX A times X equals to B, and vector B is given by the following. It's the transpose of 1, 2, minus 1, 0. So vector B is 1, 2, minus 1, 0 in a column. And now, the first thing to apply is to find the modified vector B by multiplying it by the permutation matrix. So the final permutation matrix we obtain is this one. And this is the initial vector. This is our vector B. So now it's very simple to calculate. 0 times 1 plus 0 times 2 plus 0 times minus 1 plus 1 times 0 will give us the first element. The second element, 1 times 1 plus everything else is 0, so it's 1. The third element is 1 times 2, which is 2. And the fourth element is 1 times minus 1, which is minus 1. So this is the updated B vector. And now we will start with the forward forward substitution procedure. Okay. So the first step will be to calculate the value of D, vector D. Okay, how to calculate vector D? I go back. I need now to solve for U times, as you know, as we said, okay, we defined in our case, after writing L times U times X equals to P times B, we defined U times X as being vector D. Okay, and we will now solve for D. To solve for D, we will use which equation? We will use L times D equals to B prime. Okay, so this is vector B prime. Vector B prime, we found it by doing P times B. It's 0, 1, 2, minus 1. So now we will go up to use the matrix to find D. Let me check your questions. Okay. So if I go up to L, this is my L matrix. Okay, I have that L times D. So D is unknown. I will write it as D1, D2, D3, D4. Okay, equals to a vector B. I obtain the modified vector B prime. So let us write it here. Okay, B prime is 0, 1, 2, minus 1. So here we have 0, 2, minus 1. Sorry, it's the modified one. And 0, 1, this one. Okay, I will take P times B, which is 0, 1, 2, minus 1. Okay, and now I will go back to L times D equals to B prime. So here I have L. What I will do now is the following. Okay, I will start with the first equation. Why I will start with the first equation? We call it now forward substitution, because here in the first equation, this matrix is a lower triangular matrix. So all elements here above in the upper part are 0. So I can benefit from this by starting with the first equation. Then I will have just 1 times d1. So d1 equals to b prime 1. And b prime 1 is 0. Okay. So this is equal to 0. So I got the value of d1. Now I can move to d2. So to find d2, I will go to the second equation. Okay. If I the equation, the resulting equation will be, so now equation 2 will be 0.1818 times d1. But since d1 is 0, I can directly substitute, plus 1 times d2 equals to which element now? This equation will be equal to what?
1.
1, exactly. I take the second term of b prime equals to 1. So now I will get d2. d2 is equal to 1. Now I can move to calculate the value of x3. To calculate x3, I will move to the third equation. So now I will have, okay, I will have to write 0.2727 times d1, but d1 is 0. I directly replace, so times 0, plus 0.125 times d2, and d2 is 1, so directly I replace, plus 1 times d3, so plus d3 equals to 2. Okay, so now I get the value of d3. And finally, okay, I have the fourth equation will be minus 0.1818 d1 minus 0.2361 d2 minus 0.1503 d3 plus d4 equals to b prime 4. I already have b prime 4, d1, d2, d3. I get d4. This is called the forward substitution. Now, once I am done, now vector d is completely known. Okay? Once vector d is completely known, now I can say, I can go back to the definition of d is u, the matrix u times x equals to d. So now I will move to backward substitution, because now I have an upper triangular matrix times vector x equals to d. So I will go to a backward substitution to solve for vector x. So let us see it here. Now we will write just here, this is the upper matrix. Okay, this is our upper matrix. We multiply it by vector x, so x1, x2, x3, x4 equals to vector d, which was already calculated, and we have found already that d1 is 0, d2 is 1, and we replace d3 and d4 by their values. Okay, so we know them. Now we will proceed in the backward way, okay, because هي upper matrix is this one, it's the final one, this one, after getting all elements in the lower part equal to 0. Okay, so now we will start by the final equation, because now zeros are from this side, from the lower side, not from the upper side. This is why we will do here backward substitution. So by starting with equation 4 here, equation 4 will give us just 8.3252 times d4, sorry, times x4 equals to d4. And since d4 was already calculated in the previous step, so I can get now x4. Once I get x4, now I can move to the third relation, which I will get from row 3. From row 3, I have minus 8.5 x3 plus 2.625 x4 equals to d3. Okay, and I will repeat this procedure until solving for all my x's. So I start with x4, then with x3, then with x2, then with x1. So this is called now the backward substitution because I started from equation 4 to equation. Okay? Any question on this? So as you can see it here. After doing this operation, you can verify, please try to do it as practice and verify that the x vector will be as follows. It's the transpose of this row vector. So x1 is 0.1079, x2 is minus 0.1403, x3 is minus 0.2385, and this is x4. Okay. Now, we have
دكتور
seen that, yes?
بس البيفتنج ده الماتريكس ما فهمت كيف بنعملها.
Okay. The pivoting L matrix is very simple. يعني مثلا in the first step ما بنعمل شيء لأنه already ما عندي ولا element. Okay. Now in the second step بدك تنتبه البيفتنج ما بتعملها لكل الرو، بتعملها بس للموديفايد elements. يعني طلع هون بال you have it in the two، تنقول in the second step or we in the third step, let's say we did pivoting of these elements of the third and fourth rows. Okay. إذا بتلاحظ هول ال 101 هول ما بنعملهم pivoting لأنه always the lower matrix بده يضلوا ال ones على diagonal. So you forget pivoting will only be done على lower part. Okay. يعني ال upper part will remain as it is عندي على diagonals ones وعندي zeros in the upper part. Just I will pivot the elements in the lower part. يعني بما انه you want to pivot rows 3 and 4. Okay. يعني ال elements اللي كانوا هون ال elements in red بيصيروا تحت وال elements in green بيصيروا بال third row. Okay.
Yes, okay, دكتور.
Any other question on this? Okay. So now, if you remember when we defined LU factorization, we said that one method, okay, one method to perform LU factorization is to do the Gauss elimination. And as we do the Gauss elimination, we can find a lower matrix will be constituted by factors F used for Gauss elimination. So, and as I told you, it is one of the possibilities. Yani, it's not the only way to decompose the matrix into a lower and upper matrices. Okay, so one technique is to perform Gauss elimination and then to fill L in the same time by the factors used in Gauss elimination. We have several other methods. Okay, one very efficient method is Cholesky factorization. But the problem with Cholesky factorization is that it cannot work on any matrix. We have conditions. Whenever these conditions are met, we can apply Cholesky factorization. What are these conditions? The conditions to apply Cholesky factorization are the following. First, the matrix should be symmetric. And second, it should be positive definite. Okay, so we will see what is the mean of symmetric and what is the mean of a positive definite matrix. Okay, so to start with, what is a symmetric matrix? It's very simple, the concept. So first, the symmetric matrix should only be a square matrix. It cannot be, what do we mean by square matrix? Do you know? When we say it's a square matrix, this means that the number of rows is equal to the number of columns. Okay, so we cannot have different numbers of rows and columns. Okay, the second criterion, yes, Hassan, it's right, n times n. The second criterion is that to have asymmetric, we should have matrix A is equal to the transpose of itself. So matrix A is equal to transpose of A. This means that if I switch rows and columns, I still obtain same matrix. So if I have any element aij in the first should be when I do the switching to get the transpose, when I do for any element I switch rows and columns, this means that if I consider aij, it should be equal to a transpose of ji. Okay, and then if I have a symmetric matrix, I will get the same matrix exactly when I do the transpose. It's not the case always. It's just for a in case when I have a symmetric matrix, I will have then a equals to 80. Okay. هلا في يكون عندي a equals to 80 وما تكون symmetric. So you should pay attention. We have two conditions: تكون square matrix and تكون symmetric. Okay. So let us do examples on this to understand it better. So for example here, if you take these possible matrices, how you can check if it's symmetric or not? You can just by just looking at it, you can know. If you take the diagonal elements, you should have a mirror with respect to the diagonal. So here, for example, it's not a symmetric matrix. This one, you don't care for diagonal elements. They can be anything. They should not be the same. They should be different. They can be different or they can be the same. I don't care for them. Okay, I just look at if the diagonal is a mirror or not. So here it's a mirror, it's symmetric. Here's the same. If I take the elements, I can see that the diagonal is a mirror, so it's symmetric. And here also. Okay. Now, in this example here, it's not the case because you can stop from the first elements because -2 is different than 2. So it's not a symmetric matrix. Here, it will be, of course, 2, 2, 1, 1, -2, 2. So it's symmetric. Let us take the other definition. And instead of doing it like this as mirror, the second definition, first condition is to have it a square matrix. For example, here, it's n by n, 3 columns, 3 rows. So the first condition is satisfied. Second condition is to have the A equals to the transpose of A. So if we try it, okay, we will get that, let us do it. So 0 to 1 will become 0 to 1. So the first row will become the first column. 2, 0, -2 will become 2, 0, -2. And also, if I do 1, -2, 1, so then I will get exactly the same matrix. So A is equals to transpose of A. So I can say that it's a symmetric matrix. Okay. Now, in general, the rule is that if I take the transpose of the matrix, I will get the same value. Okay, the same matrix. Now, the second condition is to have that matrix A is positive, definite for any vector x. What do we mean by matrix A is positive, definite for any vector x? So if I consider, for example, x transpose times A times x positive, okay, then how can I demonstrate this? I will start from any vector. So for example, here I want to prove that this matrix 1, 0, 0, 1 is a positive definite matrix. Okay. If I want to prove this, I should start from any vector x. So I put random values A and B. Now, why here I selected 2 rows for x? Because we know that when we do A times x, what is the condition to make it possible? We should have the number of columns of A should be equal to the number of rows of x. So since we have 2 columns for A, then we should have 2 rows for x. Okay. Now let us try to verify this equation. So we will start first by calculating A times x. To do so, we will do it in detail. So first, starting by A times x, we will replace the matrix A by its value, which is 1, 0, 0, 1, and vector B by AB. And then if we proceed, we have the result will be 1 times A plus 0 times B. So for the first row, it's row element, it's A. And for the second row element, it's 0 times A plus 1 times B, it's equal to B. So now you can say that A times X is replaced by vector AB. And now the second step is to then multiply the transpose of X by the result of A times X. So now I get that AB row times AB column is the result of X transpose times A times X. And this is equal to A square plus B square. Okay, and this is positive. Okay, so whatever is X, إلا إذا X 0 0 يعني. But any other value, we will have a positive positive value for A square plus B square. So we can say that our matrix is positive definite matrix. Okay, so now if these two conditions are satisfied, symmetric matrix and a positive definite matrix, we will develop together a method that will allow us to factorize in a much easier way our matrix. And to introduce this method, okay, we will see what we should do. So just here, since A square plus B square is positive, then the matrix is positive definite, and we can use the Cholesky factorization to divide it into a lower times upper. Now, before introducing Cholesky methods, let us consider another example of a positive definite matrix. So if they gave us the following matrix, okay, first you can verify if it's symmetric, because here you have -1, -1, 0, 0, -1, -1. And another way to verify that it is symmetric is to switch rows and columns. So if you write the transpose of A, the row 2 -1, 0 will become the column 2 -1, 0. -1, 2 -1 will become -1, 2 -1. And finally, 0 -1, 2. So the matrix A is equal to its transpose. So we can say then that it's and the number of rows is equal to the number of columns. It's a square matrix. So it's a symmetric matrix. Okay. So the first condition is satisfied. The second condition to check is that we have for any vector x different than 0, 0, 0, xt times A times x is positive. So we will take vector x ABC, okay, and we will try to prove that for any vector x, أكيد الvector 0 0 حيعطيني 0. You know, this is why I am saying for a vector different than 0. Okay, so for any vector different than 0, I should verify that xt times A times x is higher than 0. So to verify this, we follow the same procedure. In the first step, we multiply matrix A by vector ABC. So we get the first element will be 2A minus B plus 0 equals to 0. So the first element is 2A minus B. The second element is minus A plus 2B minus C. And the third element is 0 times A minus B plus 2C. Okay, so now I will multiply this result. This is A times X. And please pay attention for the order of multiplication. You cannot commute in matrix. Okay, and when you deal with matrices, you cannot compute. Okay, you cannot commute. So now we will take the transpose of X, which is ABC, times the result we got from A times X. And it will be very simple to calculate now. We will just obtain a number. So we just do A times 2A minus B plus B times minus A plus 2B minus C plus C times 0A minus B plus 2C. Now, our purpose is to demonstrate that this is always positive for A, B, C, D, the three different than 0. So To do so, I will try to rearrange my to do the expansion and rearrange my terms to put it in a way of summation of squares. In this way, I can prove that it will always be positive. So to do so, I will expand and I will get the following result. Now I will try to combine these elements in a way to create squares. And you know that the familiar expansions that you know are that a plus b square is equal to a square plus b square plus 2ab. And a minus b square is equal to a square plus b square minus 2ab. So I will try to have terms in the following form if possible. Okay, so this is why here I have here 2a square. I decomposed it into a square plus a square. I have here minus ab is minus 2ab. 2b square, I decomposed it into b square plus b square, and this is minus 2bc, and 2c square, I decomposed it into c square plus c square. In this way, you can see that I have terms that can be joined together. So a square minus 2ab plus b square can be replaced by a minus b square, and b square minus 2bc plus c square can be replaced by b minus c squared. Therefore, I end up with the summation of square terms, which is, of course, which is positive. Okay. So now I can say I demonstrated that the matrix A given is a positive definite matrix. Okay. Any question on this part? So now,
Doctor,
yes,
can you go back one slide?
yes.
Can you just remind me كيف عملنا ال multiplication تبع transpose مع الماتريكس؟
Yes, sure. Okay. Your vector x is ABC. It's a column vector. Okay. When you say transpose of x, so it's a row. It becomes A, B, C in a row. So this is x transpose. Okay. And now concerning A times x, you understood how we obtained this number, this column
Yes,
vector?
this is here.
Okay. So now you are multiplying a matrix with one row with a matrix with one column. So your result will be a number, because when you multiply a matrix A by a matrix B, okay, the result will have the same number of rows of A and the same number of columns of B. Okay, and since your A matrix has one row and your B matrix has one column, yani the result will be one row, one column, yani one number. Okay, now how to obtain this number? You just multiply A, the first element of the first matrix, by the first element of the second matrix, plus the second element of the first matrix times the second element of the second matrix, and plus C times, which is the third element of this row, times the third element of this column. So you'll obtain just one number. Okay?
Okay, thank you.
Welcome. And now, once we are done with this, we can verify that my matrix is positive definite. Now, how I can benefit from this? So already I proved it's symmetric, okay, because A times it's a square matrix, and A times A transpose is A is equal to A transpose, so it's a symmetric matrix. And I proved that it's a positive definite matrix. So now all I have to do is to define what is the Cholesky decomposition and how I can benefit from these properties to facilitate the factorization process. We have seen that LU factorization is better than Gauss elimination when we have several, we are changing the vector b, and when b is variable. But also still LU factorization needs time. So how we can reduce this time? We will come up with this technique, which consists on saying that any matrix that verifies the following conditions: symmetric and positive definite, okay, will be decomposed using the following method. I can say that A can be written as L, a lower matrix, okay, a lower triangular matrix times the transpose of this lower triangular matrix. Or also, second definition is that it can be written as the transpose of an upper triangular matrix times the upper triangular matrix. These two are equivalent, and you know that the transpose of an upper triangular matrix will give you a lower triangular matrix. Okay, so now let us use this definition to see what will be U. So how can I find U in a way that U transpose times U will give me A? Okay, and you are not responsible of proving that when it's symmetric and positive definite, then we can apply Cholesky. We just tell you that whenever a matrix A is symmetric and positive definite, then we can apply Cholesky decomposition, and we can write it in the form of U transpose times U. Now, what will be the elements of U? We will derive it together. To find what will be the elements of U, we will start from the definition of a matrix that can be used in Cholesky decomposition. What is the equation? The equation is that matrix A is equal to the transpose of an upper triangular matrix times this upper triangular matrix. So this is the general form of an upper triangular matrix. It's U11, U12, U13, 0, U22, U23, 0, 0, U33. Okay. To obtain its transpose, all you have to do is to switch rows and columns. So row 1 will become column 1 in the transpose. So the first column in UT is U11, U12, U13. The second column is 0, U22, U23, and the third column is 0, 0, U33. Okay. Now, next step, I will try to find what are these elements. How many unknowns I have? I just have 6 unknowns. U11, U12, U13, U22, U23, U33. I want to try to find them function of the coefficients of A. To be able to do this, I will use the equality. So this matrix is equal to this product. So let us do first the product and then compare the terms of A to the result of the product. If I do the product, the first element will be U11 times U11 plus 0 times 0 plus 0 times 0. So it's U11 squared. This is the first element. Now, if I want to determine what is the second element, so I do the product of the first row with the second column, because this term is, if you want, we can call it, let's say it's A. This should be equal to A 2, 1. Okay, yes, because we are multiplying